now we really get into a very big topic, the gradient. So we're not going to worry about that right now. So far, back in last class, we were looking at finding the rate of change either in the X or the Y direction. Well, that only covered two possible directions, right? As you can imagine, at any given point in a plane, there's 360 degrees worth of directions we can go in. There's infinitely many directions. So we want to be able to find the rate of change in any direction. And that's what we're going to work on today. Now, it can be difficult to find rates of changes in other directions by just trying to look at a contour plot, because it's very difficult to determine what your change in output is with respect to your change in input. You have to do a whole bunch of measurements. Because you're not going along the X or the Y, it gets very, very messy. But it turns out that this can actually be broken down very nicely. This is we're going to go through this because there is something I want to show you in here. All right, so let's say we've got a unit vector, we'll call it U. And this is our notation. This is a notation for a directional derivative, F sub U, with the vector hat on it. This is our old limit definition applied to directional derivatives. This would be a mess to do by hand, but it is going to lead us to something better. And what this will do will give us the rate of change of F in the direction of U, where U is any unit vector. That'll take care of the issue of being confined to just the X or Y direction. I want to take a look at how we can calculate this using a little bit of trig and something we just talked about, because something's going to come out of this that is very interesting. Actually, a lot of things come out of this that is very interesting. I know we don't do a lot of derivations in here, but this one I think is worthwhile. So we'll just start with a plot. And this is going to be our point, AB. And let's say that's our unit vector U. That's the direction, some arbitrary direction that we want the derivative in. Okay. Now we got to match it up with our limit definition. So just like all the way back in Calc 1, H is some arbitrary distance that we're eventually going to let be 0. Okay. So let's just put it to about there. Let's say that's H. And we've got our limit definition. So F in the direction of U at AB is the limit as H goes to 0 of F of A plus H U1, comma. This is just the definition. You do not need to know this, but there's something I want to show you. All over H. Okay. So basically what's happening is we're looking at the change between the output at this point and the output is this arbitrary point as H goes to 0. That's the idea. All right, well, how can we make this something that we can work with? Well, let's get in our right triangle and we'll call this angle alpha. Now, what we have here are basically our change in X, or dx, and our dy. It's going to be some right triangle trig. We have our adjacent side. So this is H cosine alpha. This is our opposite side. So this is H sine alpha. Now here's where things get really cool. This is a change in output. Okay, great. Why is that useful? Well, remember what we just talked about 5 or 10 minutes ago. The differential can give us an estimate in our change in output. So This thing here can be approximated by our differential of f. That's huge for us. In fact, they're going to be exactly the same once h does go to 0. So, limit as h goes to 0 of f sub x dx plus f sub y dy all over h. Now again, this is the numerator. That's just the differential we were talking about last time. What does the differential do? It gives an estimate in the change in output. Well, because these are going, h is going to go to 0, this thing is going to be exact. Now, let's also combine what we put in over here. So limit as h goes to 0 of f sub x h cosine alpha plus f sub y h sine alpha all over h. Something very awesome happens here, right? All the h's cancel. And that is now our limit. F sub x cosine alpha plus f sub y sine alpha. This gets better. We can break this into the dot product of two vectors. Specifically, fx comma fy dotted with cosine alpha sine alpha. Now, some really cool stuff going on here. Number one, this is a unit vector because cosine squared plus sine squared is 1. So the square root of that is 1. So we know the magnitude of this is 1. So this is a unit vector in the direction we were interested in finding the derivative in. That means it preserves direction, but gets rid of the magnitude. So there's our unit vector in our direction. This is just a vector made up of our partials. You know, I'm probably going to say it a few times today. If you can take your partial derivatives, you can find this vector. It's just made up of the partials. There's nothing crazy going on here. X goes first, y goes second. This vector has a special name. Happen to know what it is? Just this vector by itself. I'll give you a hint, it was in the title. Here is the gradient. Never take that long to give me that answer again. Guys, the gradient is, as far as how easy it is to find, because it's just a gradient, it's just a vector made up of the partials, it's probably one of the most powerful things that we have in all of calculus. I'm not saying it's the most powerful overall, but with respect to how easy it is to find, it is extremely powerful. The gradient is going to come up again and again for the rest of the semester. So the gradient is part of, now this whole thing is the directional derivative. The gradient is used to find the directional derivative. All right. And all you have to do is take your gradient and dot it with a unit vector in the direction that you're interested in. And we'll do an example of that later. But I just want to kind of really beat home the importance of the gradient. There is a link, and it should be actually, I think it's on today's calendar page, to a website I like called Better Explained. And they have an intuitive approach to the gradient. So if you get a chance, check it out. They have some really cool stuff on their site. I'll link it a little later with some of the other topics that we'll get to that may feel a little bit abstract at first, but are really powerful. So this gradient is going to be big for us. If you can find partial derivatives, you can find the gradient. That's the best part. That's what we worked on. That's why we spent time working on that last time. If we have our partial derivatives down, we can find tangent planes, we can find differentials, we can find gradients, we can find directional derivatives. Everything falls out of that. So if you want everything above this line, you can forget about it. That's fine. It was just to show you where it came from and to introduce you to the gradient. This is what we need to be able to do. All right. Let's talk a little bit about this gradient fella, because like I said, it is a big deal. And when I say it's a big deal, I'm certainly not trying to scare you. It is easy to find and it is easy to use. It's almost like you think it's wrong because it's so easy. So we're going to talk about the gradient by itself, and then we'll talk a little bit about it combined with the directional derivative. Again, it's a vector made up of the partials. That's it. If you can find partials, you can find a gradient, and they go in order. This extends to n dimensions. However many variables you can have a gradient for it. We're only going to do it in 2D and 3D. But if you had a function of 4 variables, you could find a gradient for it. All right. This I wouldn't worry about too much, but it talks a little bit about the relationship between the directional derivative and the gradient. Now, more often than not, this is going to be the form that you're going to see the right here. Yes, the upside down triangle is the notation for the gradient. This is saying the gradient of f at the point AB. So that's all the gradient, and getting dotted with u, where u is a unit vector, that's the directional derivative. So, you know, on the board, I have cosine alpha, sine alpha. Just switch sides. Yeah. Oh, oops, I didn't mean to. Thank you. Like we talked about before, very rarely will we do vectors in terms of an angle unless that's what we're given. Most of the time, we'll have vectors in terms of components. But all we care about is that it's a unit vector. We preserve the direction. We want to get rid of the magnitude. The next part is if you're dotting it along the x-axis, well, then you get the partial with respect to x. Well, that makes sense. That's the direction you're going in. You dot it with a vector along the y-axis, you get f sub y. Nothing crazy going on there. All right, just a couple properties fall out of this. This was our geometric definition of the dot product. Remember, it relied on the angle between two vectors. Now, we know that the magnitude of the unit vector is 1. So really all it boils down to is the magnitude of the gradient times cosine of theta. Well, that means when theta is 0, these things are going to be at a maximum. That's going to be a really important idea, because that means that the gradient points in the direction of maximum rate of change, because our directional derivative is a maximum if our unit vector is in the same direction as our gradient. All right? So this is how powerful the gradient is. It's the vector that points in the direction of maximum rate of change, whose magnitude is the maximum rate of change. And all we have to do to be able to find those things is find the gradient. A lot of ideas that we talked about are going to come back into play. So that's our max. The min is if they're in the opposite direction, because it's 180 degrees the opposite direction. So if the gradient is the fastest we can go up, then the 180 degree opposite direction is the fastest we can go down, and hence the min. If they're perpendicular, then the directional derivative is 0. And all this should make sense based on the stuff that we talked about before with our level curves. So let's talk about that. So let's say we have a gradient. Well, remember, we said we would want to be moving perpendicular to a level curve to be moving up or down as quickly as possible. The gradient points in that direction for us. It's always pointing in the direction of increasing f. To get the steepest descent, you would just put a negative in front of your gradient and go the opposite direction. Oh, and lastly, remember, if the angle between you and the gradient is 90 degrees or pi over 2, they're perpendicular. Well, remember what that would mean. That would mean we're walking along a level curve, so we have no rate of change. The magnitude of the gradient is the maximum rate of change. That's it. So if you ever asked to find the maximum rate of change of a multivariable function, you find the gradient and you find its maximum. Like we said before, it's large when contours are close together, the magnitude, small when they are far apart. Guys, this is nothing new. You told me this stuff. So I'm now taking the stuff you told me when we looked at level curves, and we're just applying it to the gradient, which gives us something concrete where, hey, give me a function. Now I can find the direction of steepest descent and what that maximum rate of change is. I'm not going to spend a lot of time on this. All this stuff, and don't worry about taking notes on this. All this stuff applies in 3D as well. The derivation is a little bit messier than what we did up there, which is why we're not even going to bother doing it. But everything else holds. So if you have a function of 3 variables, if you want to do a directional derivative, it's the gradient dotted with the unit vector in the direction that you're taking the derivative. Same exact definition. Nothing changes at all, except for one small interpretation, but all this is still the same. The max, it still gives the maximum rate of change. The negative of our gradient still gives the steepest descent, direction and magnitude. And finally, again, if they're perpendicular, it's 0. Now, here's one last thing I want to talk about. And we're going to take a look at why this is kind of interesting here in just a second. So when we had a function of 2 variables, the directional derivative is 0 if we're moving in a direction tangent to a level curve, right? We've talked about that because then there's no rate of change. We're not changing height, right? It's kind of like if you're going on a trail around a mountain, if that trail doesn't go up or down, you keep you have no rate of change. Yep. And the gradient is perpendicular to that because that'd be your way to go up to the next level or down to the next level as quickly as possible. With a function of 3 variables, it is analogous, but we remember we no longer have level curves, we have level surfaces. All right. So in 3D, the gradient gives us a vector that is normal to a level surface. So that's a difference we want to that we're going to take advantage of. Let's see on this next problem. All right, so let's do a tangent plane together. There's something I want to show you. All right, I said before, if you can find partials, you can find a tangent plane. Well, everything, if we remember the formula for a tangent plane, f of AB plus f sub x at AB times x minus a plus f sub y minus b. So, okay, so if you guys didn't hear John Paul, he said f of 1 comma 1 is 4. Everybody okay with that? That seem reasonable? Okay, so we're already one piece there. We only need 2 more pieces, really. We need f sub x at AB and f sub y at AB. Well, first let's find them. What's f sub x?
Negative 2x minus. No, it's just
The
negative
y drops
2x.
out. The y will drop out, right? Because it's a constant.
Yeah.
And f sub y is?
2y.
All right. And then we need them at our point, right? F sub x at 1, 1 is, and f sub y at 1, 1 is negative 2. Very good. That's it. We're done. Our tangent plane is z equals 4 minus 2 times x minus 1 minus 2 times y minus 1. All right. That's how quickly we can find a tangent plane if we know how to take partials. That's it. All right. Now, I want to rethink this idea of finding a tangent plane because sometimes this will be useful. What we're going to do is make our function a level surface of a function of 3 variables. Specifically, it'll be the level surface of the function 6 minus x squared minus y squared minus z. And we'll just say when it equals 0. All right. So W, we got 6 minus x squared minus y squared minus z. Now, remember what we were just saying? For a function of 3 variables, the gradient actually gives us a normal vector to the level surface. So we're specifically going to let this be the level surface when this is 0. And what we'll do is we'll find its gradient. Okay, well, we just go through and take the partials. Minus 2x, minus 2y, minus 1. Now, we are going to evaluate this at our point 1, 1, comma 4. So we're going to think of this as an ordered triple now. And we're going to plug that point into here. So the gradient of W is minus 2, minus 2, minus 1. Now remember what that last slide said. The gradient is perpendicular to the level surface at this point. All right, well, that means what we have is a normal vector. We have a point, then we can find the plane in point normal form. Does that sound familiar? Oh, yeah. And so that's going to be minus 2 times x minus 1, minus 2 times y minus 1, minus 1 times z minus 4 equals 0. Now, the question could emerge, okay, well, geez, are these the same plane? Well, let's do this. I'm going to distribute that minus 1. So minus 2 times x minus 1, minus 2 times y minus 1, minus z plus 4 equals 0. Then I'll add that z over to the other side, right? Just to save a little time, we put the z over. We get the exact same thing we had before. So it's another way of finding a tangent plane is to treat the function of 2 variables as a level surface of a function of 3 variables and finding the normal vector and then doing point and normal form of a plane. Depending on what you're given and what you're working with, one way may be easier than the other. But again, this is really to drive home the point that what the gradient gives us for a function of 3 variables is a vector that is perpendicular or normal to the level surface. And we can see that clearly because it gave us the exact same tangent plane by doing the point normal form. Questions about that?
Not yet.
All right, and I want to do one. Together from the 13.5 worksheet, just to give us a little bit of practice and bring this thing home. We're gonna look at number 4 here. And I think a lot of it you guys are already going to be able to do, but I just want to go through a couple of things. So we're going to look at number 4. So while I'm erasing, if you want to start on A, feel free. So we have f of x, y, z equals 100 minus x squared minus y squared minus z squared. It's not a really difficult function. All right, well, if I want to find the gradient at 3, 4, 5, what's the very first thing I'm going to need to find? I'm going to need the partials. So, gradient of f, what are the partials?
All -2 variable.
Okay, so we have minus 2x, minus 2y, minus 2z. All right, now we should be able to find the gradient of f at 3, 4, 5, which is going to be minus 6, minus 8, minus 10. You know, yeah, okay, we could get some functions that might be, the partials might be a little messy on, but procedurally, this is very doable for us. Okay, B wants a directional derivative in the direction of V. Now, we are going to take a dot product. We've already done part of the work for this, but what do we need to do before we take the dot product? The vector V, because remember what we want to do, we want to preserve the direction, but get rid of the magnitude. So the very first thing we'll do is we'll make V a unit vector, which will have the -2, the 3, and the 1. But we have to divide by the magnitude, which is the square root of the sum of the components. So 2 squared is 4, 3 squared is 9, 13, plus another 1 squared is 14. Square root of that. You can't forget that part, otherwise this thing will not come out correctly. The directional derivative is a scalar. The gradient is a vector. Okay, so now for the directional derivative, so up in the direction of u, we have our gradient, so minus 6, minus 8, minus 10, dotted with so -2, 3, and 1. The 1 over rad 14, you can keep it in there. You can put it along the components. Again, our final answer is going to be a scalar. Over rad 14. And then remember dot product. Just multiply corresponding components. So what do we got? We got 12 minus 24 minus 10. So when all said and done, we have 1 over rad 14 times -22. So -22 over square root of 14. Like I said, directional derivative is a scalar. That is the rate of change at the point 3, 4, 5 in the direction of V. Questions about V? C, find the maximum rate of change at 3, 4, 5. What do I need to do? What gives me the maximum rate of change? The magnitude of the gradient. So the maximum rate of change is going to be the square root of, because you're going to be squaring them, you don't have to include the negatives, but what do we have? 36, 64, and 100?
Yeah.
So square root of 200?
Yeah.
You want 10 square root of 2? That's it. We're done. Remember, the gradient is that powerful. It gives us all this stuff. A vector in the direction of maximum rate of change. I'll give you a hint. We already have one on the board. What's a vector on there that would point in the direction of maximum rate of change? And think about what just gave us the maximum rate of change. Gradient. It's just this. It's just -6, -8, -10.
Oh, that's what I meant by F, so.
Well, f sub u was this directional derivative, which came out to be a scalar.
Oh, yeah, sorry.
That's okay. No, these are the differences that we have to get down. You know, that f sub u, that's not a vector. What this is saying is it's the function taking the derivative of the partial of f in the direction of u. Whereas when we label a vector, well, this is gradient. Gradient gets the upside down triangle. Otherwise our vectors always have a hat on them. But again, you know, we actually got asked the same thing twice in this problem. A and D are the exact same question, just asked different, well, have the exact same answer, just asking about this different aspects of the gradient. You can have the gradient placed on there. Now the gradient's 0 because we're at the top point, but if I move that point around, you can see how the gradient changes depending on where the point is. That red arrow is the gradient that is pointing in the direction of maximum rate of change, and its magnitude is the maximum rate of change. In fact, notice when the point is on a steeper part of the curve, the vector is longer, and if it's more shallow, it's shorter. So you can, that's just on this drop-down menu if you ever want to add a tangent plane or a gradient. You can also add normal vectors and some of the other stuff, but yeah, so that's what the gradient does. And like I said, what's great about it is if we can find partials, the gradient isn't a problem to find.
Got it.
The reason I want to go through this problem is it's actually a very easy problem, but it may not look like it initially. The other reason is because, you know, as you guys prepare for the midterm, one of the things you want to keep in mind is going back through the worksheets and looking at some of the problems in the worksheets. That'll give you some good extra practice for the midterm. Like I said, if you look at the midterm review, it kind of give you a bit of a study plan for the exam. And we'll talk about it more next week, and I'll be able to take some questions. Well, let's take a look at this number 7 on the worksheet. Okay, so suppose as you move away from the point 1, 2, 4, the function f increases most rapidly in the direction of 0.6i plus 0.8k. And the rate of increase in this direction is 7. At what rate is f increasing as you move away from 1, 2, 4 in the direction of ijk all over rad 3? Okay, so it's not the most straightforward way to ask a question, but think about what it's asking. We're looking for a rate of change in the direction of a given vector. That should bring to mind a directional derivative. So, two things we need to find the directional derivative. We need the gradient, and then we need a unit vector in the direction we're interested in. Remind me, what does the gradient give us?
Maximum change.
Gives us its magnitude is the maximum rate of change, and its direction is perpendicular to what?
The vector.
What vector?
Unit vector.
What unit vector? There's infinitely many vectors. It's perpendicular to a very specific. If we're going to use vectors to a very specific vector, yes, it's in a direction that's perpendicular to a contour line, or we could say to a tangent vector to a contour line. It points in the direction of maximum rate of change, and its magnitude is the maximum rate of change. So if we look at what this problem gives us, it gives us the direction of maximum rate of change. So 0.6, 0.8. If you find the magnitude of that, it's 1. So that's actually a unit vector that's in the direction of the gradient. And it says the maximum rate of change is 7. So that's the magnitude of the gradient. Oh, I won't be in the fall. I know. We can't complain too much since there's not that many of us, but it's not the right room for us. Okay, sorry. Back to what we're talking about. The gradient of f is 7 times, we could write it in either form since I like bracket form, 0.6, comma 0, comma 0.8. That is the gradient. Now, we need a unit vector in the direction we're interested in. If we were to find the magnitude of this vector, 1 squared plus 1 squared plus 1 squared is 3. Square root of that is rad 3. This is a unit vector in the direction that we're interested in. So we don't have to do anything there either. So really, all we have to do in this problem is dot product the two of these vectors together. And dot product's commutative, the order doesn't matter. So we end up with 7, so our directional derivative is 7, 0.6, 0, 0.8, dotted with 1 over square root of 3. Bless you. 1. Now, I'm just going to take the 7 over the rad 3. Now, as a reminder, the gradient is a vector, but a directional derivative is a scalar. It comes from the dot product, so it should just be a single number. So what do we end up with? We end up with 0.6 times 1 plus 0 times 1 plus 0.8 times 1.
So that's just
1.4.
0.6 plus 0.4.
Okay, and if we multiply that by 7, that's what, 7, 9.8.
Yep, I'm going to.
So I wanted to go through that one because it's the reverse of what you've been doing. And a lot of them, it was like, okay, here's the function, find the vector of maximum rate of change. Okay, so we find the gradient. Find the magnitude of the maximum rate of change. Find the magnitude of the gradient. In this case, we were actually we weren't given the function, we were actually given the gradient, but in terms of what it gives us. And I really want you to take that relationship going forward, which is why I wanted to go through this one with you. Again, it doesn't take long, but the first time you see it, it's asked in a very different way. So it's really trying to build that connection of what the gradient gives us. Remember, it's super easy to find if we're given a function. It's just the vector made up of the partials. But we really also want to take away what is it. So when the question asks, okay, give me a vector in the direction of maximum rate of change, we know, like, oh, just the gradient. Or if we're asked for a directional derivative, it's the gradient dotted with a unit vector in the direction we're interested in.